determining the mass of a black hole. The objective of this lab was to determine the mass of a black hole using position data of a nearby star. This was accomplished by creating a computer model based on Newton's laws. Newton's law states that when an object is moving, an unbalanced force is acting on it. And so in this lab, we are given position data that shows our star is moving around a black hole. So if we figured out the change in position over change in time, we'd figure out the velocity. And then we could figure out the change in velocity by taking a final velocity minus an initial, and we did that many times to figure out the change in velocity. And then we can figure out the momentum, which is delta p, by taking the change in velocity times the star's mass. And then to figure out the net force, it's the change in momentum over change in time. So the net force can be broken into two component parts, the parallel portion of force, which changes the acceleration, and the perpendicular portion, which is going to change the curvature or make it curve. And the change in momentum over change in time can also be broken down into the parallel and perpendicular portions, and that can be seen in the last equation on this slide. So the net force is due to the force of gravity, or the attraction between the black hole and the star, and the force of gravity is proportional to g, the mass of both of the objects, and the distance between them squared. G is equal to 6.67 times 10 to the negative 11th. And using all of this, we figured out that the mass of the black hole was 2.53 times 10 to the 31st kilograms. Okay, so here's my coding, and in the code, I actually had the computer program determine the mass of my black hole. So what I did here was added in a visualization for the black hole, and you can see that coding in blue. Now in purple, you can see my star's mass, which was 2.6373 times 10 to the 27th kilograms. And I also put in the position of the black hole again so it could calculate the mass of it for me. The change in time was 86,400 seconds, or it's the time equal to 1 day, and the time started at 0. Here you can see some of the coding for the actual calculation loop. In gray, we have the calculation for the initial momentum and the final momentum. And again, the mass of the star times the velocity. Then in red, you can see the change in velocity and change in momentum, and just taking the final velocity minus the initial and the final momentum minus the initial. So then we have the change in momentum over change in time, coding in orange, which is delta p divided by delta t. And then in yellow, it shows that the net force is equal to the change in momentum over change in time. The green portion is the portion that shows the force that is parallel to the motion. And then in purple, it shows the force that is perpendicular. And we know that the perpendicular force plus the parallel force is equal to the total force, which is the change in momentum over change in time. So here, to figure out the perpendicular force, we did the change in momentum over change in time minus the parallel component of the force. Calculating the mass of the black hole. Again, I used the gravity equation, and you can see here highlighted in blue is the coding that I used to do that. And I'll show you the printed out version of it in a second. Here is the actual program, and you can see the yellow arrow is the net force, the black is the parallel, the blue is the perpendicular. Okay, this is what the statements that I printed out in order to figure out the mass of the black hole. And we printed out the magnitude of the force and the parallel component and the perpendicular component, and then the mass of the black hole. And you can see the mass of the black hole is highlighted in purple. And from the WebAssign, I just picked up that it showed that the calculation was correct. The difference between FNet and the change in momentum over change in time is that the change in momentum over change in time can be calculated from observations, where FNet actually causes the motion and cannot be measured directly. Therefore, FNet is qualitative and dp dt is quantitative. What if? What if the original black hole was replaced with a new one, but the position and motion remained unchanged? Could you tell? The answer is no. Since the motion remains constant, the mass of the new black hole must be the same, so no, we could not tell that it was a new black hole. And in conclusion, the position data was used to make a computer model that was based on Newton's laws. The computer model did correctly predict the mass of the black hole.